Have you ever wondered why the color wheel your art teacher taught you doesn't match the color wheel on screen? And how do you find the right complementary color when every tool seems to give you different results? To figure out why, let's explore how colors are mixed. There are 3 different systems of color mixing. The first is what you probably learned in grade school. Red, blue, yellow are your primaries, and mix pairs of these to get your secondaries. We call this subtractive color mixing because we're blocking out or subtracting certain wavelengths of the spectrum when we mix pigments together. This is a good all-around system because it works across a huge range of opaque materials, from oil and acrylic to colored pencil and pastel. The second set of primaries is what printers use, cyan, magenta, and yellow. The CMY primaries are a cousin of the first set and are a more accurate set of primaries for subtractive mixing, so long as the pigment is transparent. Use inks, watercolors, or even oil color glazing, and you can generate cleaner, more predictable secondaries than with the more traditional RYB primaries. The third and final set of primaries are red, green, and blue, RGB, like what your monitor uses. These are used in additive color mixing, called that because we're adding or combining multiple wavelengths of the visible spectrum to produce a new apparent color. So again, 3 sets of primaries, RYB for opaque pigments, CMY for transparent ones, like inks and glazes, and RGB for the digital world of projected light. You probably know that if working with paint, to find the complement, you travel 180 degrees to the opposite side of your color wheel. Begin with red, and your complementary color is green. If using CMY or RGB, we do the same thing, but this means we don't get green as our complement, we get cyan. Which one is correct? While RYB is a practical system that emerges from how pigments mix, if we arrange color by the wavelengths of light, then cyan is the more accurate complement of red. But let's go even further in RGB space and see if we can fine-tune our color complements to be as precise as possible. Again, we'll start with red and move 180 degrees around the circle, but this time we'll match our starting color in both lightness and vibrancy. For this, we'll use OKLCH, a model that we can apply to RGB so that the colors are arranged according to human vision rather than strict quantities of light. Now, a 30-degree rotation around one side of our wheel is the same relative color change as a 30-degree rotation around the other side. Additionally, any change in lightness or vibrancy is equal no matter the direction you're moving in. This means by using OKLCH, we don't just land on a generic cyan, we get this specific shade of cyan, one that naturally harmonizes with our red rather than competing with it. If you want to explore this color space yourself, I'm using Volume, a color tool built on OKLCH, where you can find precise color complements or build entire palettes that are perfectly calibrated for human vision.